what are we likely to see in a distribution of a sample of size 15? What can we say about that distribution? You haven't heard it? Yeah, so it's specifically where one tail of the distribution is longer than the other. Um, okay, so let's talk a bit about. Do you just want me to go over some details about skew first? So, so just to review some things about skew. Um, a skewed distribution is where one of these tails is longer than the other. And the mnemonic I like to use for this is you can imagine this as like a playground slide. So we have the ladder going up one side, the steeper side, and then the direction that you ride the slide is going to be the direction of the skew. So this is um, a right skewed or positive skewed distribution that I just drew. And the mean is more heavily influenced by skew than the median is. So um, the mean is drawn more in the direction of the skew. And if we see that the mean is less than the median, this implies that we have a negatively skewed distribution. If the mean is equal to the median, this suggests that we have a symmetric distribution. Meaning no skew. And if the median, sorry, the mean is greater than the median, this is a right skewed distribution or a positively skewed distribution. So here I say that we have a positively skewed population, and we take a sample of size 15. And what we can say about this sample is that um, since this is a pretty small sample size, we likely have um, a mean near 15. I'll just say around 15, and variance around 4, but not necessarily very close. Um, since n is small. And what do you think we can say about the shape of this distribution? If the population has positives. What can we say about it? Okay. Um, so I would say here that we are more likely to have positive skew than negative skew. But since the sample size is small, the sample um, data distribution does not necessarily look like the population. So we might have positive skew, but we might have a different shape because 15 is not many observations. Now, part B, I'm asking about a sample of size 100. So now we have a larger sample, and I want to know what is the shape and some attributes about this larger sample. So what do you think we can say about this? What was that? Sorry. In what way? Okay. So with this size 100, we can say that the mean is likely quite close to 10 and variance quite close to 4, since n is fairly large. So the larger our sample size, the more likely we are to see that mean and variance be approximately what the population is. And in terms of the shape, this distribution very likely has positive skew, since the shape of large samples, and this is not an enormous sample, but it's pretty large, is similar, I'll say is usually similar to the population. Now, we have a small chance that the distribution of our sample doesn't look like the distribution of our population. There's always that possibility, but the bigger our sample size, the more that sample is going to be shaped like the population, the more likely it is to be shaped like the population. Does that make sense? Okay. And we can also say here that the, oh, sorry, this should have been 10, not 15. We can also say that the median is very likely less than 15 because of this skew. So that's just referencing what I was talking about up here. Okay. And now C and D, I'm asking not about a about the distribution of a sample, but the sampling distribution for X bar. Is the difference between those clear to you? X bar is not equal to mu. X bar is a random variable. So actually, I should, really, these should have been capital X bar for each of these rather than lowercase. If we're following the notation, capital letters denote random variables. Sure. So for A, I can't exactly draw what A is going to look like because I don't know. There are a bunch of possibilities here. Let's say I draw here the population might look like this here, and our mean is 10. For n equals 15, we could have something that looks like this, or something that looks not at all like the population. Or we could have something that looks quite like the population. So because our sample size is small, we've got more variability there between those. And really, this 10 should be up a little bit farther. Because like I said, that mean is getting drawn in the direction of skew. Sorry. With B though, since we had, so n equals, actually, leave that there. Since we had a larger sample, we can more reliably say that our sample is going to look like our population. So we can be pretty confident that it looks like this. Now, part C, we are asking about the sampling distribution for X bar. So I'll say we are interested not in the distribution of a single sample, but in the distribution of possible values for X bar itself. So our sampling distribution is if we take a bunch of samples from this population that all have size 15, what does the distribution on those X bars look like? And the distribution will have a mean of 10. And I'll actually just say has a mean of 10. And a variance of 4 divided by the square root of 15. Because some facts about the sampling distributions. And add a page after this. There's some stuff around. Oh, this is fine. Okay. So some properties of sampling distribution. That I'll actually just say sampling distribution for the mean. Is that for small values of n, the I'll say for continuous distribution specifically, and small values of n, the sampling distribution will look somewhat like the population, just narrower. For large values of n, so looking at the sampling distribution of the sample mean from large samples, the sampling distribution, and I'll say just looks, because this is something that we can actually describe if we know the population. It may not be elegant, but if we know the population, we can always find the sampling distribution in theory. And for large values of n, the sampling distribution is approximately normal due to the central limit theorem. Assuming that the mean of the population is defined, which is going to be virtually every distribution you ever see, although there are some exceptions, like the Cauchy distribution does not have a well-defined mean. And in terms of mean and variance of this, we can say that the expectation of x bar, which is to say the mean of our sampling distribution for the sample mean, is just going to be the population mean. And the variance of x bar is going to be the population variance divided by n. Oh, sorry. And so this should have been just not square root 15. This should have just been. If we're looking at standard deviation, we have a square root. But for the variance, it's just sigma squared divided by n. And so that's why I say what I said here. And we can also say that the distribution will look like a narrower version of the population, assuming that our population is continuous, or approximately continuous. So comparing to what we had up there for the sketch for B, with this one, we will still have a bit of a left skew distribution, but it's going to be compressed towards the center. And I'll say it looks somewhat like a narrow version of the population because if the population is skewed, the skewness of the sampling distribution for that sample mean decreases as n increases. So the larger sample we have, the less skew we're going to see in that sampling distribution. Does that make sense? Okay. Um, this is sort of reference in the start of your notes, I think, because we mhm. Yeah, so this one is the sampling distribution for X bar with n equals 15. And you discuss this I believe in the notes. You talk about expectation and variance of the sample mean. I don't see the page number, but the one that starts with sampling distributions up top. Um, but this is just a good thing to like have an intuition for, and you see these sorts of questions in more more introductory statistics courses like to ask this as a um, yeah, it's talking about the sampling distributions up at the top, and then it says for any distribution with mean, mu, and variance sigma squared, the expectation of our sample mean x bar is mu, and the variance of our sample mean is sigma squared over n. And so this is the expectation and variance of the sampling distribution. Does that make sense? N is the sample size. Are you familiar with n representing the sample size? N is just the variable we use, or not, or Mhm. So I mean you can't see the sample size on the plot here. The sample size is um, not the sample size of this distribution, but the sample size of the sample means that go into this distribution. Because if this is our sampling distribution, that means that this is like, you can think of all of our possible values of X bar if I take a whole bunch of samples from my population. All those possible samples, I look at their sample means. That gives me the sampling distribution. And the variance I said was 4 over 15. So you can't exactly draw variance on the plot, but the variance is the variance is the average squared distance from the mean, and that's our measure of spread. So if we compare what I'm drawing in pink here to what I'm drawing in pink up here, which this was, I labeled it as I said that this is the approximate distribution we would expect for a sample of size 100. But that's the same shape and width as the population distribution. We can say here that the spread of the distribution of the sampling distribution is narrower than the spread of the population and narrower than what we would typically see in a sample from the population. Because again, this is the distribution we're seeing here, not an individual sample. This is basically a summary or an aggregation of all of the values of X bar that we could get from taking many, many samples from the population. Does that make sense? Okay. So even with n equals 15, we see a narrower distribution than our population itself. But when we go to n equals 100, we really get a nice looking distribution. Hold on, Zoom is causing problems for me. Okay. So when n equals 100, we can apply the central limit theorem to say that the distribution of the mean will be approximately normal, even though the population itself is positively skewed. So any distribution you want with very limited exceptions is going to be relevant for the central limit theorem in that if we take large enough samples from that distribution and look at, for instance, here we're talking about a bunch of samples of size equals 100, the distribution of those sample means is going to be approximately normal. And I'll draw that here. So if 10 is in the same spot as it was before, I'm going to get a very narrow distribution that is centered right there at 10 and is approximately normal. So I'm not, I said this one had left skew. I'm just going to take this and squish it. That's approximately symmetric for this purpose. But we'll have that very narrow normal distribution for the distribution of the sample mean from samples of size now 100. And the distribution still has a mean of 10 and a variance, or sorry, the variance is different now. The variance is still 4 over n, but now that n is larger, it's going to be 4 over 100. So that variance has come down drastically from our original population. And all this is to say that when we are taking samples of size 100, we're going to get very precise estimates of our population mean, and we're going to have a good idea of what the shape of that distribution is. Sorry, I need to. Do you have any questions? Oh, sorry. I was letting my dog in. Um sorry if I didn't say that clearly. Um I want to write the density function for this uniform distribution, right? So do you remember what the uniform density is? If we know our lower and upper bound for the distribution, what is my density function here? You know? You're muted right now. Um, what I'm asking about first is the density function for x. So are you familiar with the density function? Are you familiar with density functions in general? Um, let's say, do you know what a density function is or how it's used? Okay, so um, yeah, I'll add another page here. Density functions. We can say that continuous random variables are defined using density functions. They can be defined in other ways, such as the cumulative distribution function or the moment generating function. But most often you'll see the density function. And density functions must be non-negative everywhere and must integrate to 1. As long as those two conditions hold, you've got yourself a valid density function. And the probabilities, um, yes, yeah. But probabilities can be computed from the density by integrating. So I can say that the probability that first I'll say that if small f of x is the density or PDF for my variable x, then the probability that x is between two values here, which I'll say is just to emphasize something about continuous distributions. This is the same thing as this quantity here, which is the same thing as this which is the same thing as this. So whether you're looking at a less than or a less than or equal to makes no difference for continuous distributions. Because what we're doing is finding the area under the curve between the bounds that we're looking at, A and B. And so we can integrate here from A to B, our density function f of x dx. And that gives us the probability. So let's say we are looking at oops. Perhaps our distribution looks like this, where this in blue here is the function f of x. And if we're looking at bounds, let's say here is A and here is B. Then the probability that x is between A and B is area in green. What I'm shading right now. And that's a proportion of the total area, because the area of the whole curve, because what I drew in blue is a density function, has to be 1. And so any areas that I'm looking at over only part of that curve are going to be some fraction between 0 and 1. Some decimal value. Does that make sense? Of course. And while we're at this, let's look at expectation and variance in terms of the density. So we can define expectation as the integral of x times f of x dx. And if you see something like this where it's an integral, but the bounds of integration are not written, you can assume that it's over the entire domain of x. So we can integrate from negative infinity to infinity, or whatever our bounds are. And because outside of those bounds, this is just going to be 0, so you can integrate it and it's just 0 over the leftover parts. And the variance of x, we can say is the expectation of x minus mu x, which is our expectation for x itself squared. Or in other words, the expectation of x squared minus mu x squared. This first thing we can write as the integral of x minus mu x squared f of x dx. The second thing we can write as the integral of x squared f of x dx minus mu x squared. Do you have any questions about this? So going back to uh, mhm. Yeah, so going back to the uniform distribution, this is probably on your table of distributions, but the density function is equal to simply 1 over b minus a, wherever um, x is between a and b. So what I'm writing here is an indicator function, which is telling us, or its value is going to be 0. Sorry, give me a second here. Its value is going to be 1 whenever this is true. So whenever x is between a and b, and its value is going to be 0 otherwise. So this is a more succinct way of writing that the density function evaluated at x is 1 over b minus a whenever x is between a and b and 0 otherwise. Does that make sense? Um, that's a 1 with 2 bars. That's just a common way of writing the indicator function. You'll sometimes see it just written as a 1, but I find that confusing. So I do this, people call this blackboard bold. It's just you put another line on it to make it bold. And that denotes the indicator function. And then it's, no, because it's not literally a 1, it's the indicator function. So um, the indicator is defined as, oops, I should say, I'll just write it in the same form we have here. Actually, I'll write this as condition. So this is equal to 1 if the condition is true, which in this case is to say that x is between a and b, and it's equal to 0 if false. So the reason we can't remove it is because we need to be able to express that this density is 0 everywhere outside of the interval between a and b. Does that make sense? Okay. And so some properties about this. The expectation is a plus b over 2, so just the middle between a and b. And the variance is 1/12 b minus a squared. And you can show both of these things using the property that I talked about on the previous slide by just integrating this density function. And so we're looking here for the maximum likelihood estimator of the expectation of x. And So for this particular, for this particular distribution here, my density function is equal to 1 over b minus a is theta minus 0. So it's just 1 over theta times the indicator for x being between 0 and theta. And if we're looking at the maximum likelihood estimator for expectation of x, we first want to find the maximum likelihood estimator for what value? If we want the MLE for the expectation of x, what do we need to get the MLE of first? Theta, exactly. And this is because if let's say that theta hat is the MLE for theta, then how do I write the MLE for expectation of x? Which I'll label that mu hat. How do I write mu in terms of theta hat? So the expectation of x is a plus b over 2. And for us, what is the value of a for this particular example? It's 0, yeah. And what is the value of b? Exactly. So we just plug those in and we get that the MLE for the expectation is theta hat over 2. So now it comes down to finding the MLE for theta hat. But I am out of time for the session because I've got one at the top of the hour. So I will send you a Google Doc that will have the Zoom recording from today, as well as this document you're looking at now. And I'll see you tomorrow at 6 o'clock your time, right? 11 Eastern? Okay. Thank you, Yusuf. Have a good one. You too. Bye-bye.